In this work, we consider the problem of learning simple estimation on 4D radar point clouds using cross-modal supervision. Our motivation is based on the fact that self-driving driving cars today are equipped with multiple heterogeneous sensors, and we argue that such collocated perception redundancy can be used to provide supervision cues for radar simple learning. We propose a cross-modal supervised learning pipeline for 4D radar simple estimation. A multitask model architecture is introduced for the identified problem. We retrieve various supervision cues from 3 collocated sensors and train the model end-to-end using cross-modal constraints. We demonstrate the state-of-the-art performance of our method and show its effectiveness in downstream tasks as well. Here are some demos showing our qualitative results. Thanks for watching the quick preview. Now let's go back to the beginning of this presentation. In this work, we consider the problem of learning point level simple estimation on 4D radar point clouds. You may want to know, what's point cloud SymFlow and what's 4D radar? SymFlow is a 3D uplift of optic flow from the image plane to the 3D space. For point cloud-based SymFlow, the inputs are 2 consecutive point clouds. The outputs are point-wise 3D motion vectors that present the interframe displacement of each source point. In autonomous driving, the SymFlow can be induced by the motion of both ego vehicle and objects. Point cloud SymFlow can provide holistic motion cues to multiple downstream tasks, such as ego motion estimation, motion segmentation, multi-object tracking, and point cloud accumulation. 4D automotive radar is an emerging sensor technology in the automotive industry. It received increasing attention recently due to its advantages over LiDAR and camera. It's robust against adverse weather and poor lighting conditions. It has 4D imaging functions. It's kind of radar on shape with low cost, small size, and lightweight. To learn simple estimation on point clouds, one challenge is that the acquisition of simple annotations are costly. In literature, there is a trade-off between the annotation efforts and the model performance. So we'd like to ask how to overcome such trade-off. That's getting a high performance with low or no annotation efforts. Another challenge comes from the radar point cloud, which suffers from the sparsity and noise. This further complicated the simple annotations and makes self-supervised based methods unfeasible. To find a more effective framework for 4D radar simple learning, in this work we aim to exploit cross-modal supervision signal in autonomous vehicles. For example, we can estimate odometry using SymFlow of static points. The consistency between the odometry estimation and the observed odometry from GPIs INS can be used to supervise our model learning. A similar consistency can also be found between the optical flow from camera and the perspective projection of SymFlow. However, retrieving accuracy supervision signals from collocated sensors and effectively use them is non-trivial. For example, the depth and via perspective projection potentially incurs weaker constraints to the SymFlow of far points. This motivates us to consider the following research problem: how to retrieve the cross-modal supervision signals from collocated sensors on a vehicle and apply them to collectively bootstrapped 4D radar simple learning. The contribution of this work can be summarized in 3 points on this slide. The overall pipeline of our proposed method SymFlow can be seen on the slide. Our model is designed in a 2-stage fashion, with a rough initial SymFlow derived in the first stage, and refined in the second stage to obtain the final estimate of SymFlow. It can deliver the solution to 3 different tasks, and these outputs are compactly correlated to each other. A key step in our pipeline is to retrieve the cross-modal supervision signals from 3 collocated sensors on autonomous vehicles. It can support model training without human annotations. These cross-modal supervision signals are utilized to constrain our outputs with various loss functions. In the ego motion loss, we use the odometry to supervise our estimate rigid transformation. By supervising the rigid transformation, we can also implicitly constrain our initial and final simple output. To supervise our motion segmentation results, we leverage both odometry and LiDAR 3D MOT results to generate a reliable saddle label, and we supervise the moving and static points separately to balance their impact. To constrain the syncflow vectors or moving points, we generated saddle syncflow labels with the help of LiDAR and odometry. We also use the saddle optic flow labels from RGB images to supervise our syncflow in the perspective view. In our experiments, we compared syncflow with 7 baselines that also demand no annotation efforts for training. SAMFlow shows remarkable improvement on all metrics by leveraging cross-modal supervision signals for training. We also conduct ablation studies and show the impact of different modalities. We also analyze the causes of noisy supervision signals from camera and LiDAR. We further mix in an extra amount of unlabeled data for training to see the change of our performance. After adding only 20% of actual samples, SAMFlow can already outperform PV Raft trained with less annotated samples. Here are 2 SAMFlow demos showing our qualitative results. It can also be seen that our method can give accurate SAMFlow predictions in different scenarios, very close to the ground truth. We also evaluate the motion segmentation prediction of SAMFlow and analyze the impact of 2 gradients of the saddle motion segmentation labels. 2 motion segmentation demos can be seen on the slide. Our method can segment moving points belong to multiple dynamic objects in complicated scenarios. At last, we evaluate our ego motion output and show the ablation study results. We also accumulated interframe ego motion between frames and show the odometry results. As seen in our demos, without any global optimization, our method can provide accurate long-term trajectory estimation in dynamic sense. By only estimating interframe transformation, our method can remarkably outperform the SAP baseline. Thanks for watching this representation. If you want to know more about our work, please scan the QR codes on the slide.